So this is the 29th lecture. In the last lecture, I discussed conductivity with you, and conductivity in general for a conductor. Conductivity for a conductor I discussed with you is sigma is equal to mu into n into E for a conductor, and then I described it for a semiconductor n mu n plus p mu p into E. Then for intrinsic semiconductor n is equal to p is equal to ni, this is equal to this much, and then for n type semiconductor as for p type semiconductor. Now let's discuss let's do some problems based on this first of all, then I'll move to next article. So the first numerical that I'll discuss with you here is a numerical. First problem is this. This is a problem or a numerical problem which says calculate the conductivity. It says that calculate the conductivity. What you have to find is the conductivity. This is what required. You have to find the conductivity. Calculate the conductivity of a pure silicon. Pure means intrinsic silicon. So I need the conductivity of an intrinsic silicon at room temperature when the concentration of carriers, now carriers can be either electrons or holes, but in case of intrinsic semiconductor you have a number of electrons is equal to the number of holes, and it is given by intrinsic concentration Ni, and this is given to you concentration of carriers, this is given to you Ni is 1.6 into 10 to the power 10, 1.6 into 10 to the power 10, this much charge carriers per centimeter cube. This is the data which is given to you. Given that the mobility of electron, is 1500, this is what mobility of electrons means. Mu for electrons it is n. This is given to you 1500 centimeter square. 1500 centimeter square, and the mobility of hole, this is the mobility of hole, that is mu p, is 500 centimeter square per volt second, and this is 500 centimeter square per volt second. Now it is asked to calculate the conductivity of pure silicon. So conductivity of an intrinsic semiconductor, I know that conductivity of an intrinsic semiconductor, I derived this with you in the last lecture, it is equal to Ni, intrinsic concentration, into mu n plus mu p, this factor, into the electronic charge E. So I substitute the values. Value of Ni is 1.6. This is 1.6 into 10 to the power 10. This is given to me. Mu n is 1500 plus 500 into value of E. This value of E is electronic charge, that is I know it is equal to 1.6 into 10 to the power minus 19 coulomb. 10 to the power minus 19, 1.6 10 to the power minus 19. You simply solve this equation and I can if you solve this, okay, let's solve it. It is equal to 1.6 into 10 to the power 10 into, this is 2000, into 1.6 into 10 to the power minus 19. If you solve this, approximately I give you to find out what is the value of this. It is conductivity per ohm, this much per ohm per centimeter. This will be the final answer. I want to do this calculation on your own. So this is how you solve this problem. Next problem. Look at the next problem. Calculate the density of impurity atoms that must be added to an intrinsic silicon in order to convert it to this much. First part is this much n-type silicon. So you have to make n-type silicon. It says that calculate the density of impurity. Density of impurity for n-type, of course it is the donor impurity which is asked. That is, what is the value of Nd? What is the donor concentration, or what is the donor impurity per unit volume that must be added to an intrinsic silicon crystal to convert it to a 10 to the power minus 4 ohm meter. Now if you see, look at this unit is ohm meter, means resistivity is given to you. This resistivity is given to you, it is equal to 10 to the power minus 4 ohm into meter. Now try to understand what this problem is. It says that you have a silicon atom, a pure silicon, and you add some donor impurity to it. You add some donor impurity to this. The resulting semiconductor is a N-type silicon. And the resistivity of this N-type silicon is given to me this much. It is asked that what amount of donor impurity that must be added. Calculate the density of impurity atom. Very first thing is to understand the problem. So in other words, what you have to do, you have to find ND for this. Now I know that and of course it is given that mu n is equal to this much and mu p is equal to this much. Second part I'll deal later on. So if you see, look at the solution of this. I know that conductivity of a N-type semiconductor, if you remember, it is approximately equal to, in general, it is equal to mu Ne. So it is, for this, it is be mu n. N-type means mu n into Nd into the electronic charge E. This is the conductivity, and resistivity is equal to 1 upon conductivity. So I can say that this resistivity is given to you 10 to the power minus 4. This will be equal to 1 upon this factor. This is equal to 1 upon mu n into Nd into E. Or from here I can say that this resistivity is given to me 10 to the power minus 4. 10 to the power minus 4 is equal to 1 upon, what is mu n? From here mu n is 0.138 into Nd. I have to calculate, and value of E, if you see, value of is 1.6 into 10 to the power minus 19 coulomb. And if I solve this, if you simply solve this, you will find the value of Nd. I want you to calculate the value of this Nd. This much meter cube you can say. So sigma is equal to mu Ne. In place of mu is equal to mu n, in place of n, a number of electrons, number of charges will be approximately equal to donor concentration into E. So this is the conductivity, but resistivity is given to you. Similarly, look at the next problem. To make it this much p-type silicon, you have to make it a p-type silicon. Second part of the problem, I want to do it on your own. So what is asked here? Density of impurity atoms. In this case, what is asked is Na. You have to find the value of Na in this case. Find the acceptor concentration that must be added in order to make it a p-type. Next it says silicon to be added with a acceptor impurity, and that concentration of acceptor impurity is asked. I want to do this part on your own. Second part, first part I have done with you. Do these calculations and find the value of this. I hope that this is clear to you. Next, I'll take one more problem, last problem. Next numerical. Calculate the current produced. Next problem says, calculate the current produced in a germanium plate. There's a germanium plate here. I'm taking, okay, I'll take this way only. Let's take the cross section of this. Germanium plate of area 1 centimeter square. The cross sectional area of this. Cross sectional area, it is given of area 1 centimeter square. It is 1 centimeter square. I can say it is equal to 1 into 10 to the power minus 4 meter square. And thickness, that is the length of this. If this is given to you, it is the length of this, or the thickness of this, you can say it is equal to 3 millimeter. L is 3 millimeter. 3 millimeter. I can say it is 3 into 0.3 rather, not 3, it is 0.3. So 0.3 into 10 to the power minus 3 meter. When a potential difference of 2 volt is applied, a potential difference of 2 volt, it says the battery of 2 volt is applied. A potential difference of 2 volt, that is V, is 2 volt is applied across its faces. Given that the concentration of free electrons, now it is a pure germanium again, concentration of free electrons, I can say that N. which will be equal to P and which will be equal to Ni. It is equal to 2 into 10 to the power 19 per meter cube. The concentration of free electron is 2 into 10 to the power 19 per meter cube, and the mobility of electron and holes, mobility of electron, that is mu n, is given to you. It is equal to 0.35 meter square per volt second, and mobility of electrons and holes, mobility of holes, that is mu p. Mu p is given to you 0.17 meter square per volt second, and it says calculate the current produced. All I have to do is to find the value of current. This is what is required. Now for a conductor, if you remember, I told you that this I for a conductor is equal to N E into Vd, where Vd is the drift velocity, and this factor into A. This we derived while deriving the value of conductivity. If you go into the previous lecture, you'll find it. It is equal to this much. Now, of course, for a semiconductor, when I say drift current for a semiconductor, current for a semiconductor, I can say, I'm writing SC, for an intrinsic semiconductor, will be the current due to electrons, and of course it will be equal to the current due to holes, the current due to holes. Now the current due to electrons or current due to holes, if I generalize this, for example, suppose I'm not writing this right now, let's find it for a conductor only. This current is equal to, I can say it is equal to N into E into Vd is equal to mu E. In place of this drift velocity, I am applying that this drift velocity Vd is equal to mu E, Ne into mu, or I can say that this is equal to N is equal to P is equal to Ni. I know for intrinsic semiconductor this N is equal to P is equal to the intrinsic concentration Ni, so I can say it is equal to Ni intrinsic concentration into electronic charge into mu, leave this mu as it is, and this is equal to V by L. This E is equal to potential per unit length, and this length is given to you this much. Now if you see, if I say for semiconductor, what will happen for semiconductor, this Ni will remain same, this E will remain same, this voltage applied is same, this length of the conductor is same. All I have to do is to replace this by mu n plus mu p for this. So far I can say that the current produced in this semiconductor is equal to Ni into E into, in spite of mu, that is what I am doing, this plus this, it will be mu n plus mu p, N into E into V by L. This is equal, this is V by L. I hope that this is clear to you. It is equal to Vd N A. This A is remaining. Okay, let's write this A also here. Vd Ne into Vd. Of course A is here. I'll write this A also. It's missing here. This A also and this A also. I hope this is clear to you. Now everything is given to you. If you see this Ni, I write it here. This Ni into E, I am writing this equation again. That is, the current in case of this semiconductor will be equal to Ni into E into mu n plus mu p into V by L into A. Now whatever all these parameters are given to me, I substitute the value of these parameters. Value of Ni which is given to me, Ni is 2 into 10 to the power 19. So this is 2 into 10 to the power 19. Value of E I know, it is equal to 1.6 into 10 to the power minus 19. Mu n, if you see that this mu n is 0.35 and mu p is 0.17. So it is 0.35 plus 0.17. Then V is the applied, this capital V is the applied voltage. Capital V, the applied voltage is 2 volt. I substitute this value. This is 2 into cross-sectional area is 1 into 10 to the power minus 4, and the length of this is 0.3 into 10 to the power minus 3. If I solve this, I have done the calculation, but I want you to cross check it. It is approximately equal to 1.31 ampere. So I hope that this problem is clear to you. First of all, what I have done is that all these parameters I have extracted from this problem, and I know that this current I is equal to NE into VD into A. But this is for conductor. In case of semiconductor, you have current due to electrons as well as current due to holes. I expand this. All I have to do is the mobility due to electrons and mobility due to holes here. Had it been an extrinsic one, then I had to take the electron concentration as well as the hole concentration. In this case, electron concentration and hole concentration is equal to same as Ni. So there was no problem in this. So here I have done few problems with you based on this. I'll discuss some more problems. But before coming to some more problems, let's take one small article, that is called the mass action law. For semiconductors, or it is also called the law of mass action. In some of the books it is written as law of mass action. Now what does this law of mass action says? First of all, try to understand this. What it is, I have told you that you have an intrinsic semiconductor. Suppose I say that this is an intrinsic semiconductor. This is a intrinsic semiconductor. Now this intrinsic semiconductor, in this intrinsic semiconductor, number of electrons is equal to number of holes, and it is equal to Ni. That is, I say, if these four, simply I say, these are the number of electrons, then these are the number of holes. This is an intrinsic semiconductor. Let's talk about the extrinsic semiconductor. Suppose I say, when it is doped, say N-type. When I say it is N-type semiconductor, for a N-type semiconductors, electrons are far greater than the number of holes, hole concentration. And for P-type, holes are far greater than the number of electrons. Now it says, just try to understand, it says that when an intrinsic semiconductor is made N-type, the number of electrons increases. Number of electrons increases and the number of hole decreases by a considerable amount. And when a system is made P-type, when a semiconductor is made P-type by adding some impurity, of course the number of hole increases, but the number of electrons decreases by a considerable amount from its intrinsic value. In this case, in N-type, the electrons increases and hole decreases by a considerable amount with respect to this intrinsic value. And in case of P-type, the holes increases and electron decreases by some amount as compared to this intrinsic value, this Ni. Now the mass action law says, if one quantity is increasing, the other is decreasing. It says that under thermal equilibrium, the mass action law says that under thermal equilibrium is under constant temperature and pressure. If the temperature and pressure are kept constant or maintained constant, it says that although one is increasing, the other is decreasing with respect to this Ni, but the product of, it says that the product of electron concentration and hole concentration, where N is the number of electrons per unit volume and P is the number of holes per unit volume. So mass action law says that under thermal equilibrium, the product of electrons concentration and hole concentration is a constant. One is increasing, the other is decreasing, but its product will remain constant, and that constant is nothing. It says that this N into P is equal to the square of intrinsic concentration, and this is the mass action law or law of mass action. I hope this is clear to you. It says that one quantity is increasing, the other decreasing, but under thermal equilibrium, the product of electron concentration and hole concentration is a constant, or it is the product of electron concentration and hole concentration is equal to the square of intrinsic concentration. This is about the mass action law. So I'll deal with the charge densities in semiconductors and mass action law in the next lecture. I'll stop it here for the time being. Thank you.